All right. Okay. Good evening, all. We'll start. Can you first confirm whether I'm clearly audible and visible? How about the audio and video? Okay. Right. 1 second. Right. Okay. Listen. So last month, we have already started matter and radiation, unit 11, and first part of matter and radiation, actually, right? About atomic nucleus, nuclear reactions, and radiation, right? We have already discussed, and today we are going to start the next part we have in radiation, that is called black body radiation, right? Black body radiation. So far we have covered atomic nucleus, fundamental particles, nuclear reactions, unstable particles, nuclear reactions, and the first part of radiation, right? Like age determination and all that, half-life, age determination, those things, right? Activity, radioactivity. Okay. Now, today we'll be starting the next part, second part of radiation, actually, black body radiation, right? So about the monthly plan here in the reverse class, by this month, by the end of this month, we'll be finishing whole matter and radiation, and upon the completion of matter and radiation, I'll be starting electricity here in the reverse class, right? And in the regular class, I'll be starting gravitational fields, right? Here we'll be starting electric fields, electricity, current electricity, and regular class gravitational fields, right? And the next S2A discussion will be on viscosity, right? I couldn't do it yesterday because I was not available during that time, and soon I will have a day, and probably it is going to be on viscosity, right? Since viscosity is already completed, right? You can get the updates through channels and join there and cover those past papers as well, right? About surface tension we have discussed all, right? The lesson is also covered, and after that the past papers are also covered in the S2A discussion. And for viscosity, probably I'll be allocating the next one, right? Viscosity and elasticity. The next one will be for viscosity, right? Yeah, those are the things. All right, and you are 22 weeks and just 1 day ahead of the exam. 22 weeks and 1 day ahead of the exam, right? And this Monday onwards, you are to start 21st week before the exam, and sooner this number is going to reduce to the powers the numbers starting with 1, right? Like 19, 18, 17, not 20s anymore, right? Not 20s anymore, right? Okay, then we'll start. As a heading, write down black body radiation. Black body radiation. Black body radiation. Black body radiation. Give me 1 second. YouTube live is working fine, right? Okay. Okay, right. Listen. So before black body radiation, let's get to know what heat radiation is. Listen. So you have some idea about heat radiation, from thermal physics, right? So tell me, what was heat radiation there in thermal physics? Thermal radiation or heat radiation? What was it? What was the idea? Heat radiation. What was heat radiation in thermal? Anyone? heat radiation or thermal radiation. We discuss on the methods of heat transfer, heat conduction, heat convection, and heat radiation. What is heat radiation? Transfer of heat through vacuum. Partially yes, but not the whole idea. Partially yes, transfer of heat through vacuum. Basically, it was transfer of heat without involvement of a medium, no? Right? Involvement of the medium is not mandatory, right? The method of transfer of heat from high temperature to low temperature without any involvement of the medium was called heat radiation, right? So if there's no medium involved, right, which means connect this with waves now, which means this wave should be progressed as an electromagnetic wave now, because electromagnetic waves are the only types of waves they can propagate without any involvement of the medium, right? Those are the only types of waves that they can propagate without any involvement of the medium. And heat radiation is transfer of heat from high temperature to low temperature without involvement of the medium, right? Which means in a heat radiation, we are going to take out one point. In a heat radiation, heat should be transferred as electromagnetic waves, no? Otherwise, there's no any possible way of transferring heat without involving the medium, right? So first conclusion is heat radiation should be transferred as electromagnetic waves, right? Because no medium is involved, right? So that is exactly what we call heat radiation is, right? If heat is transferred as electromagnetic waves, that is called heat radiation. Okay, as heat radiation, write down below. As heat radiation, write down below. Write down below as heat radiation. Write down below as heat radiation. Write down. Transfer of heat. 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 Without involvement of medium. Without involvement of medium. Without involvement of medium. Without involvement of medium as electromagnetic waves. As electromagnetic waves. As electromagnetic waves is called heat radiation. Is called heat radiation. Is called heat radiation. Is called heat radiation. Right. Then let's see what a black body is. Then we are going to connect these two. What happens in a black body? Right. Then as the next subheading, write down black body. Black body. Black body. Listen, black body is a definition. Listen, black body is a definition. Black body means something like this. That's a model. Huh? That's a model. That's a definition. Black body means if there is a particular surface which can absorb heat radiation of any wavelength, which can absorb heat radiation of any wavelength, and at the same time, if it can emit heat radiation of any wavelength, such bodies are called black bodies, right? Such bodies are called black bodies. If any surface can absorb all the wavelengths of heat radiation or heat radiation of any wavelength, and at the same time, if heat radiation of any wavelength can be emitted, such bodies are called black bodies, right? Write down first. Write down in red. Write down in red. In red. If heat radiation of, write down in red. If heat radiation of heat radiation of any wavelength, if heat radiation of any wavelength is absorbed and emitted by a particular body slash surface, such bodies are called black bodies. Such bodies are called black bodies. Listen. When it comes to a perfect black body, perfect black bodies are not really existing in real world, right? Which means a perfect black body is a hypothetical scenario, right? But we have objects, we have surfaces which are close to the behavior of black bodies, right? Now you will see those things in the coming questions we do, right? Now as an example, for questions we consider sun as a black body, right? We consider, but that is not a perfect black body. It's close enough to be considered as a black body, right? Otherwise, this is like ideal gases. This is an ideal scenario. This is like ideal gases, ideal scenario. They don't really exist, right? But for the ease of doing questions, for the ease of doing calculations, using learned theories, we'll be considering ideal black bodies, but they don't really exist in the world, right? Now, for the black body, we have something called a model. Model means to showcase the behavior of a black body, right? We have something called a model of a black body, right? That's just a model, right? When it comes to objects, sun can behave as a black body. Sometimes this bulb can behave as a black body, right? This bulb can behave as a black body, right? Or any other object can behave as a black body when it comes to questions. But repeating again, that is not the ideal or the perfect scenario, but for the questions we will consider, right? Then as an example, write down model of a black body. Model of a black body. Model. This is a model. Model of a black body. Model of a black body. Look at here. This is just a model to explain the behavior of a black body. Right. See. Listen. This is just a model to show the behavior of a black body, right? Heat radiation absorption is here. Absorption is represented by this one, and once it got on the body, right? So after several reflections, it comes out there is emission, absorption and emission, right? Through the hole, through this small hole, right? Now this is just a model. Then this hole is called a black body. Right? This whole is called a black body. Make a model. This is just a model. Just a model. Right? Then if this absorbs all wavelengths of heat radiation, and if it emits heat radiation of all wavelengths, this kind of a body, if it has this behavior, that's called a black body. And this conical projection is for the reflection of or the deviation of the straight heat radiation which comes in. Otherwise, it will leave without any reflection. No, that's why that conical projection is done. Right, take this down. This is just a model only. Otherwise, this is not a black body. This is a model of a black body. Right. So you will see what this actually means when it comes to the next part. When we go there, when we go to the next part. Take it down. Take it down. Take it down. Okay, write down below in point form. Write down below in point form. First point. First point. This is the model of a black body. This is the model. This is the model of a black body. 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 Right. Second point. The point. The point. Second point. The point. The point. Within brackets, hole. Hole. H-O-L-E hole. Within brackets, hole. Where heat radiation. Where heat radiation. Where heat radiation comes in. Where heat radiation comes in. Where heat radiation comes in. Heat radiation comes in and goes out. Comes in and goes out is only considered as 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 the black body. Is only considered as the black body. Is only considered as the black body. Right. Then Then next thing is about intensity, right? About intensity, we have discussed under intensity levels for the first time, right? And here today I'm going to discuss about intensity for the second time, right? As a heading, take down intensity of heat radiation. Intensity of heat radiation. Intensity of heat radiation. Intensity. Intensity of heat radiation. And tell me, what is the general equation of intensity? We discussed under intensity levels. What is the general equation of intensity? Anyone? What is the general equation of any intensity? What is the general equation of any intensity? Anyone? For the first time, I discussed in intensity levels. Beta functions, intensity levels. Let's see how well you have gone through the notes. What is intensity? General equation of intensity. What's the purpose of black rough surface? Purpose is black and rough surfaces are higher in absorption and emission, right? I didn't explain because it is coming up. General equation of intensity. General equation of intensity is, it goes as E equals ida equals ida equals ida, right? Equals ida. Then intensity is given by E over dA, right? This is called the general equation of intensity, E over dA, right? So when we keep this in mind, this is easier. I told you in intensity levels also, keep it in mind as E equals ida, right? Then I is given by E over dA. That is called intensity. Where if I introduce terms, I is intensity, right? E is total energy, T is time, A is perpendicular area, right? Then any intensity is defined as, listen, any intensity is defined as total energy per unit perpendicular area per unit time. That's how any intensity is defined. And in intensity levels, we have defined intensity of sound. So there we define that as total energy of sound waves, which falls on unit perpendicular area per unit time. Now here we are going to define intensity of heat radiation. Then only this word is going to change, right? That is about total energy of heat radiation, right? Simple as that. Okay, first take down the general equation. Take it down quickly and highlight this. This is the general equation of intensity. E over dA. E over dA. E over dA equals ida. Introduce terms. I intensity. I intensity. I intensity. Intensity. E. 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 Total energy. E. Total energy. E. Total energy. T. T. Time. T. Time. capital A perpendicular area, capital A perpendicular area, capital A perpendicular area, capital A perpendicular area, right? A small task, find units and dimensions of intensity. Quickly find units and dimensions of intensity. Quickly. Finding units means finding SI units, right? Finding units means finding SI units, not the fundamental units, right? Find the SI. This cannot be something new because I discussed about this thing in intensity of sound. Yeah, finally, Wm minus 2. Wm minus 2. That's a correct unit. Candela? Candela is luminous intensity. That's different. That's different. Right? Okay. Units. Units. Units of E over units of T, units of A. Right? But we have a single SI unit for E over T, no? We have a single SI unit for E over T. Then always we will go with that option. E over T. Work over time, energy over time is power. Then that is measured in watts. This is m squared Wm minus 2. Wm minus 2. Right? Then dimensions of energy over dimensions of time, dimensions of area. Dimensions of energy, ml squared T minus 2. Time is T, area L squared. L squared to L squared cancels, that is mt minus 3. Right? This is a unique dimension. Nobody has a unique dimension. Nobody in our syllabus has this dimension, MT minus 3, dimension of intensity, right? Take it down, make if any corrections, if any changes. Okay, right. As a next heading, take down next heading. Definition of intensity of heat radiation. Next heading. Next heading. Definition of intensity of heat radiation. Definition of intensity of heat radiation. Definition of intensity of heat radiation. Okay. Write down the equation and subject intensity again, like this. Write down the equation and subject intensity again. Subject intensity again. Subject intensity again. Right. Listen now. Listen. We have about two intensities in our syllabus. One is intensity of sound. Right. Two main intensities. Two main intensities. One is intensity of sound, and the other one is intensity of heat radiation. We have defined intensity of sound as total energy of sound waves, right? Incident on unit perpendicular area per unit time. And here, this is total energy of heat radiation incident on unit perpendicular area per unit time, right? Very comparative definitions, very comparative. Write down the definition in red. Write down the definition in red. Total energy of heat radiation. 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 Incident on unit perpendicular area. Incident on unit perpendicular area. Incident on unit perpendicular area. Per unit time. Per unit time. Unit perpendicular area per unit time. Per unit time is defined as intensity of intensity of heat radiation. Is defined as intensity of heat radiation. Okay. Next heading. Stefan's law of heat radiation. Stefan. I don't know. Stefan's law of heat radiation. Stefan's law of heat radiation of black bodies. Stefan's law of heat radiation of black bodies. Stefan's law of heat radiation of black bodies. Stefan. Okay, look at the board. There are two main laws in black body radiation, right? On black body radiation, one is Stefan's law, and the second law is called Wien's law, right? Based on these two laws, only we will be doing all sums here, all the calculations here, right? This is the first one, right? First, let's see what these laws are, and then we'll see what actually these laws means, right? Okay, now what Stefan says is something like this. Stefan means that's the name of the scientist. Stefan means name of the founding scientist. E over TA is proportional to T to the power 4, right? E over T is something we know. E over T. See, this is about intensity. E over T is about intensity, right? So that is none other than intensity of heat radiation. Intensity of heat radiation. What it says is that is directly proportional to fourth power of absolute temperature. Fourth power of absolute temperature of the black body, right? This is called Stefan's law. Now, when we say Stefan's law, when we write Stefan's law, we don't use the word heat radiation here again, because then again heat radiation should be defined, no? Then we will define E over TA here itself and we'll write the law. That's how law should be written. Otherwise, if you write this law as intensity of heat radiation is directly proportional to the fourth power of absolute temperature, no marks will be given. Then again, we have to define or introduce intensity of heat radiation. Now, there cannot be a definition inside a definition, right? Always when we define something, we have to go to the fundamentals and define, right? So therefore, again, we will define this inside the definition like this. Total energy of heat radiation incident on unit area per unit perpendicular area per unit time is directly proportional to, like that. Otherwise, we don't keep definitions inside definitions, right? First, take this down and highlight this. This is the law. This is called Stefan's law. Stefan's law. Write down law in red. Write down this law in red. Write down. Now again, we have to define this. We have to define this. So that's why I define about this, define this before coming to here, right? Again, we are going to define this. Write down total energy of heat radiation. Total energy of heat radiation. Total energy of heat radiation. Incident on unit perpendicular area. Incident on unit perpendicular area. Unit perpendicular area. Unit perpendicular area. Per unit time. Unit perpendicular area per unit time. Per unit time is directly proportional to directly proportional to fourth power of absolute temperature. Fourth power of absolute temperature. Fourth power of absolute temperature. Fourth power of absolute temperature in black body radiation. Fourth power of absolute temperature in black body radiation. Fine. Okay. Right here. Now, using this is how the equation is derived. Now, to make this an equation, we know we have to have a constant of proportionality, no? A constant of proportionality. Proportionate constant, right? Then as proportionate constant, he introduced sigma, right? Then sigma t to the power 4. And finally, the equation was given as E over T, right? Equals sigma A T to the power 4, right? Or the same equation is also written as Q over T, because here we have heat radiation, no? Heat radiation. Usually we put Q for heat energies, right? So therefore, either we can write E over T or Q over T, both are fine, right? We can write the equation like this, or, right? Or we can also write the same equation like this, right? Listen. Where E is, now that is coming from here, E is total energy of heat radiation, T is time. Then E over T can be defined as E over T. E over T can be introduced as a single term as power of heat radiation. Power, E over T is a power of heat radiation. Sigma is called Stefan's constant. Stefan's constant. And A is perpendicular area, T absolute temperature. Right? Okay. Start from here again and write it up to here. Right? Then you can introduce terms. EOQ. Introduce at once. EOQ. EOQ. Total energy of heat radiation. EOQ. Total energy of heat radiation. Total energy of heat radiation. Then T time T time T time. Then E over T O Q over T E over T O Q over T. Power of heat radiation. Power of heat radiation. E over T O Q over T. Power of heat radiation. E over T O Q over T. Power of heat radiation. Right? Sigma. Stefan's constant. Sigma. Stefan's constant. Capital A. Perpendicular area. Perpendicular area. T absolute temperature. Capital T absolute temperature. T absolute temperature. Right. A small task. Find units of sigma. Dimensions cannot be found because we have a temperature term here. No? We don't have dimensions of temperature for A levels. We have only MLT, right? Then we can't find the dimension. Find the units of sigma quickly. Put your answers. Put your answers to the chat. What is S, by the way? What is S in your answers? I didn't understand. How come a temperature be seconds? Huh? Okay, see, sigma. Sigma is given by Q over T, Q over T over AT to the power 4, right? Units of A, units of T to the power 4. This is what area is square meters and absolute temperature is in kelvins, Kelvin to the power 4. Then Wm minus 2, K minus 4. Wm minus 2, K minus 4. Right? Okay. Now, listen. Stefan's law is given only for black bodies, no? So, which means this law is applicable only for black bodies. But when we are using this for normal bodies, there is something we have to do, right? A modification, a small change, a modification. After doing that change, that modification, we can use this with normal bodies as well, right? Okay, let's see what it is. Write down below with a red pen. Write down below with a red pen. Above equation is valid. Above equation is valid. Above equation is valid only for black bodies. 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 Only for black bodies. Right. Next point. Keep using red. Next point. Keep using red. Therefore, it should be multiplied by. Therefore, it should be multiplied by. It should be multiplied by. It should be multiplied by simple E multiplied by simple E again, simple E multiplied by simple E again, simple E again. When it is used for, when it is used for, when it is used for, when it is used for normal bodies, when it is used for normal bodies, when it is used for normal bodies. Right now, in that case, the equation becomes this: simple E times sigma AT to the power 4, where simple E is called coefficient of surface emissivity. Right? Coefficient of surface emissivity that determines the degree to which, right, the amount to which emission and absorption of a body varies. The amount where it varies. Now, this is very much comparative to, this is very much comparative to what? Now, when I write this range, what comes to your mind? When I write this range of V, what comes to your mind? Is between 0 and 1. Is between 0 and 1. What comes to your mind when I write this range? Is between 0 and 1. What comes to your mind? Elasticity. Superb. Others? Others? Range of coefficient of emissivity is, coefficient of surface emissivity is 0 to 1. Between 0 and 1. What comes to your mind? This idea is very much comparative with a very popular and a familiar one with us. What is it? No, I didn't get what I expected yet. That's why I'm waiting. So I need your thoughts. Tell me. Send me. No one? Are you kidding me? There was only one thing so far has the same range as a coefficient. There was only one coefficient we had so far which has this range. What was it? Tell me what's the relationship between elasticity and 0 and 1, and what's the relationship between partial elastic collisions and 0 and 1, and what is the link between extension and 0 and 1, right? I need the coefficient we had having the same range. What was it? That was only one. Very straightforward. Very straightforward. I'm not asking about letter E. Right? Not asking about letter E. What's the coefficient we had having the same range? Which has the same range? Coefficient of friction. Right? Coefficient of friction. That's the only one. Right? Same idea and same concept. Same idea and same concept. Right? Not friction, coefficient of friction. Coefficient of friction. Right? More towards 1 means there is more towards rough side, roughness. More towards 0 means there is more towards a smooth side. So here more towards 1, which means that is towards black body side. More towards 0 means that is towards the normal side, right? Then the body of which E equals 1 is a black body. The body of which E equals 1 is a black body, right? Not really existing, right? Not really existing. But if there's a body of which where E equals 1, that is called a black body, right? Otherwise, this is what this range determines. The amount to which it is close to a black body. That's the idea. right? Up to which degree the given object is close to a black body, right? That's the idea. Now, in coefficient of friction also same idea, right? How close that to roughness? That's the idea. How close to the roughness? That was the meaning. Same thing, right? Elasticity, partial elastic collisions, nothing. And I don't see even a link with 0 and 1 of such ones, of such quantities, right? No link at all, right? Okay, then write down the equation and introduce E. Write down the equation and introduce E. Highlight the equation now again. Introduce E and mention the range as well. And mention the range. Right, finished. Listen. Okay, listen about E. E depends on two things. Listen, E depends on two things simply. Simply depends on two things, right? Simply depends on two things. One is, listen, one is, this is actually nature of the surface, right? Two things means two natures of the surface. One is, if a surface is black and rough, if a surface is black and rough, right, E is more towards 1. And the opposite of this is, if a surface is white and smooth, if a surface is white and smooth, E is more towards 0, right? E is more towards 0, right? E determines both absorption and emission, right? Which means black and rough means higher absorption, higher emission, right? And white and smooth means low absorption, low emission, right? About black and white surfaces, I think sometimes you have come across in O levels about emission and absorption in black white surfaces, right? Now the same idea we are taking a little bit more forward, right, with roughness and the smoothness as well, right? Now as an example, when it comes to asphalt roads, right, asphalt roads, highways, right, they are both black and rough, then heat absorption is very much high when it comes to roads. And if we think of the shoulder by the road, shoulder means the next soil layer by the road. If the road is like this, highway is like this, right, this is the highway, right, this is the highway, and here we have soil. Here we have soil, that is called shoulder, right? So when it comes to the road, that is black and rough. When sunlight incidents, the road increases temperature rapidly because that's a black and rough surface is high, and this soil is that is rough but not that black. Then compared to the road, emission and absorption of heat for the soil layer is comparatively low, right? Something like that, and about the white black thing, that's also there, but we are taking the same idea a little bit forward with roughness, higher the roughness, right, and higher the blackness, higher emission and radiation. So that's why we considered a black rough surface in the model of a black body, right, because it should absorb all heat radiation and it should emit all heat radiation, right. Highest emission and absorption is with black rough bodies, right. So after this mention this way, if a surface is, mention this way, next point, if a surface is if a surface is put a comma, if a surface is, put a comma, and as the first bullet point, write down first bullet, if a surface is, put a comma and first bullet point, black and rough, both emission and absorption, both emission and absorption is higher. So simply is higher, like this. So simply is higher, like this. So simply is higher. Second bullet point, white and smooth, second bullet point, white and smooth, both emission and absorption is lower, both emission and absorption is lower, so E is lower, like this. So E is lower. So E is lower, right? Okay, now take a red pen and write down as the next point using a red pen. Write down as the next point. If simple E equals 1, in red, a separate point. If simple E equals 1, it is called a black body. If simple E equals 1, it is called a black body. If E equals 1, it is called a black body. If E equals 1, it is called black body, right? Then as the next heading, write down black body radiation under 2 temperatures. Next heading, black body radiation under 2 temperatures. Black body radiation under 2 temperatures. Black body radiation under 2 temperatures. Okay, listen. Write down. Let's consider. Write down below. Let's consider a black body of temperature capital T1. Let's consider a black body of temperature capital T1. Let's consider a black body of temperature. Let's consider a black body of temperature capital T1. A black body of temperature capital T1. And temperature of surroundings. And temperature of surroundings. And temperature of surroundings. And temperature of surroundings as capital T2. As capital T2. Within brackets T1 greater than T2. Within brackets T1 greater than T2. Within brackets T1 greater than T2. Okay, look at here. So let's say this is the black body and its temperature is T1. And this is the outside surroundings. Surrounding temperature is T2, right? From high temperature to low temperature, right? From high temperature to low temperature, emission happens. Then emission happens like this. This is the emission, right? This is the emission. So likewise, emission, right? This is Q over T emission. And from low temperature to high temperature, absorption happens. That's also at the same time. At the same time, from low temperature to high temperature, absorption happens. Like this, absorption occurs. Absorption occurs. And this is the total Q over T absorption. Right? Now, if we write the net emission, no net absorption. Right? See? Net emission, no net absorption. Right? Now, inside this Q over T, what we have is this is a black body, sigma A T to the power 4. No? Sigma A T to the power 4. Higher the temperature, higher the Q over T. Then higher temperature is T1. Right? So therefore, emission of this particular black body is higher. Emission is higher. Now, if I write the net value, the resultant value, net value, right? Q over T total, net value. Q over T total is, right? Q over T emission minus, because emission is higher, because T1 is greater, Q over T absorption, right? Right. Now, after this, I want to simplify. What you can do is you can plug Q over T using sigma T to the power 4 and finally prove an equation for Q over T total. Right. Take this down first. Listen. Take this diagram first and then start from here. Start from here. And you can feed this equation by Stefan's equation. And finally, find a single equation. Find an equation for Q over T total using T1 and T2. Using T1 and T2 for Q over T total. Right. Give it a try. right? What happened? So is emission and absorption a type of power of heat radiation? That is a rate of heat flow, a rate of heat flow. That is all about heat transfer. Emission and radiation is a rate of heat transfer. A rate of heat transfer. That is a measurement about rate of heat transfer. Okay, plug this QOD total. Then QOD emission can be written as sigma A T1 to the power 4. Absorption is sigma A T2 to the power 4. Right? And this is Q over T total. Then Q over T total can be written as sigma A T1 to the power 4 minus T2 to the power 4. Right? Can we write the same as T1 minus T2 to the power 4? Are these two equal? Are these two equal? Quickly. Can we also write this as this? Are these two equal? Yes or no? Are these two equal? No, not at all. Right? Not at all. So you can't simplify further after this. That's it. Right? So if the black body is radiating under two temperatures, two different temperatures at once, we can use this equation. Right? E1 to the power 4 minus T2 to the power 4. Right? Otherwise, it cannot be T1 minus T2 complete 4. No. Right? T1 to the power 4 minus T2 to the power 4. Right? Take it down. Subtraction and subtracting means emission and absorption are two opposite sides of heat transfer, two opposite directions of heat transfer. Two opposite directions. Emissions are liberation and absorption means absorption. That is the heat which comes in. Liberation means, or the emission means, that's the heat which goes out. Right? Okay, write down below with a red pen. Write down below with a red pen. Both emission and absorption, both emission and absorption, both emission and absorption, both emission and absorption, both emission and absorption occur simultaneously, occur simultaneously, occur simultaneously when temperatures of black body and when temperatures of black body and environment, when temperatures of black body and environment are different. Black body and environment are different. Right. Next heading, write down variation between intensity and wavelength. Variation between intensity and wavelength. Variation between intensity and wavelength in black body radiation. Intensity and wavelength in black body radiation. Variation between intensity and wavelength in black body radiation. Intensity and wavelength. Right, within brackets write down I lambda characteristics, right? This is also called within brackets, write down I lambda like this. I lambda characteristics. I lambda characteristics. Right. Intensity with lambda. Intensity with lambda. I lambda. Intensity with wavelength. Right. Listen, this is a experimental result. Right. We don't have any equations to model this. Right. I mean A levels. For A levels, you don't have any equations to model this. So this is an experimental result. And the shape coming here is called a bell shape. This is called a bell shape. This is a bell shaped curve. And this point is called Imax. Right? And this is called lambda m. Lambda m means respective wavelength of maximum intensity. Is called lambda m. Respective wavelength of maximum intensity. Take down. And the other thing, the graph is plotted at a constant temperature, because with temperature intensity changes, intensity and radiation, everything changes, right? So this is plotted at a constant temperature. Take this down. This is not a parabolic shape. Parabolic is different. Parabola is different, right? Parabola is this, and this is a bell shape. That is called a bell shape. Because that is in a normal distribution, right? We have something called a normal distribution. When you do higher mathematics, you will learn higher mathematics, not combined maths, higher mathematics. In higher maths, you will learn something called normal distributions, right? So that's why this follows a bell shape, since there is a normal distribution. Take it down. Take it down. Right? I mean, why emission considered as? Because T1 was greater than T2. T1 was greater than T2. Okay, right? Introduce these two. Introduce Imax. Imax and lambda m. Imax, write down Imax. Imax. Maximum intensity. Imax. Maximum intensity. Imax. Maximum intensity. Imax. Maximum intensity. Lambda m. Lambda m. Respective wavelength. Lambda m. Respective wavelength. Respective wavelength. Respective wavelength for maximum intensity. 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 Imax and lambda m. Imax and lambda m. And below this, with a red pen, put an asterisk mark and write down. Put an asterisk mark and write down below this. Write down area under I lambda characteristics curve. Area under I lambda. Area under I lambda characteristics curve. Area under I lambda characteristics curve represents energy. Area under I lambda characteristics curve represents energy. Right. Next in emission spectrum. Emission spectrum in blackbody radiation. Emission spectrum. Write down. Emission spectrum in blackbody radiation. Emission spectrum in blackbody radiation. Emission spectrum in blackbody radiation. Emission spectrum. Right. Emission spectrum in blackbody radiation. Below this, write down. Before that, listen. Emission spectrum means we are going to plot multiple I lambda characteristics curves at different constant temperatures. At different constant temperatures. Right? Multiple I lambda curves at different temperatures. That is called emission spectrum. Right? Write down below. Plotting multiple I lambda characteristics. Plotting multiple. Write down. Plotting multiple I lambda characteristics curves. Plotting multiple I lambda characteristics curves for same blackbody. For same blackbody at different constant temperatures. For same blackbody at different constant temperatures. At different constant temperatures is called emission spectrum. Is called emission spectrum. Right. Look at here. Multiple I lambda curves at different temperatures. Right. When multiple curves are plotted, when increasing temperature, right, what happens is Imax increases. Right? Imax increases while lambda m decreases. Imax increases while lambda m decreases. See, now for this first curve, Imax is here. Right? For the second one, Imax is here. For the third one, Imax is here. Fourth one, Imax is here. Right? So what happens is Imax increases. But if you check lambda m of the first one is here. But lambda m of the second one is here. Third one is here. Fourth one is even less. here. So lambda m decreases. Lambda m decreases. And this is at different constant temperatures. Now, if I put some example values, it's like say 100 kelvins, right? Then 200 kelvins, 300 kelvins, 400 kelvins, something like this, right? And two observations from this, right? This is also an experimental result. Two observations from this: when temperature increases, Imax increases, but when temperature increases, lambda m decreases. Take this down. Take this down. Take it down. And your graph should properly show these variations. Okay, finish. Your graph should have the exact correct shape. And when you draw emission spectrum, listen, when you draw emission spectrum, draw minimum of 4 curves, right? Or more than 4 is totally fine, right? When you are asked to draw emission spectrum, draw minimum of 4 curves. Okay, finish. Write down below. Write down below. According to, write down below. According to the graph. According to the graph. Write down below. According to the graph. Right. Two observations we have. Right. Two observations. When temperature increases, intensity increases, no? And when temperature increases, lambda m decreases. Right. Use a red pen. Use a red pen. First point. First point. Write down. Intensity increases. Intensity increases when temperature increases. First point. Intensity increases when temperature increases. Intensity increases when temperature increases. Intensity increases when temperature increases. Fine. Then below that, write down T is proportional to I max, like this, because it is behaving proportionally. No? It's behaving proportionally. Right. Then next point. Next point. Next point. Write in words first. Lambda m decreases when temperature increases. Next point. Lambda m decreases when temperature increases. Lambda m decreases when temperature increases. Lambda m decreases when temperature increases. Fine. Then for that we can say lambda m is inverse proportional to, sorry, other way, T is inverse proportional to lambda m. Right. Take this down. Right. Then as an next heading, write down Wien's displacement law. Wien's displacement law. Wien's displacement law. Wien's displacement law. W-I-E-N, Wien. Wien's displacement law. Wien's displacement law. Wien's displacement law. Right. Through this emission spectrum, right? Wien was the scientist who found out, right? Wien was the scientist who found out this, right? Then this was separately presented as a different law as Wien's displacement law, right? So what Wien's displacement law says is this, right? T is inverse proportional to lambda m, right? This is called Wien's displacement law. Okay, take it down and highlight. Take it down and highlight. Write down below with a red pen. Write down below with a red pen. Right, we are writing the law. Respective wavelength for maximum intensity. Respective wavelength for maximum intensity. Respective wavelength for maximum intensity is inversely proportional to absolute temperature, inversely proportional to absolute temperature, in black body radiation, inversely proportional to absolute temperature in black body radiation, inversely proportional to absolute temperature in black body radiation, right? Right here. Now after this equation again, to make this an equation, a constant of proportionality was put as k, right? And the equation was stated as lambda mt equals k. Lambda mt equals k. This is called Wien's equation, right? This is called Wien's equation. Wien's equation, right? Prove it up to here. Prove it up to here. And after this, introduce these terms lambda m, t, and k. Right? Right. Introduce these terms. Label this as Wien's equation. Label this equation as Wien's equation. Introduce terms lambda m. Respective wavelength for maximum intensity. 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 Then capital T, absolute temperature. Capital T, absolute temperature. Capital T, absolute temperature. K, Wien's constant. K, Wien's constant. K, Wien's constant. K, Wien's constant. Wien's constant. Okay, a small task. Find units of Wien's constant. Find units of Wien's constant. Quickly. Find units of Wien's constant. Units of Wien's constant. Right. Units of lambda m. Units of lambda m into units of absolute temperature. Lambda is measured in meters. Absolute temperature is measured in kelvins. Right. Simple m, capital K. We don't write this as simple K, capital M usually. Right. We write this as capital K, simple m. Right. Because otherwise, if you write simple m first, right, it has a meaning like milli, no, as a prefix. Right. But that is not meant to be the prefix. That is meters. Right. So this is called Kelvin meters. This is called Kelvin meters. Within brackets, Kelvin meters. Write down this way and mention Kelvin meters. Kelvin meters. Okay, then write down next point. If Wien's equation is used for two different scenarios, write down. If Wien's equation is used for two different scenarios, if Wien's equation is used for if if Wien's equation is used for two different scenarios, put a comma and look at here. Put a comma and look at here. Right? So we know lambda m t equals k. If we use this for two different scenarios, right? Scenario 1 should be lambda m1 t1 equals k. And for scenario 2, it will be lambda m2 t2, right, equals k. Right? Now since k remains same, Wien's constant remains same, that's a constant. Wien's constant remains same. Right, we can write this equation as this. Listen, we can write this equation as lambda m1 t1 equals lambda m2 t2, right? And when we write this equation, we usually don't write m, right? So instead, for our ease, we'll be writing lambda 1 t1 equals lambda 2 t2. Right? This is how we are going to refer this equation when applying for two scenarios. Very simple. Now, as Boyle's law, PV equals K. When PV equals K, P1 V1 equals P2 V2. Charge law, V over T equals K. Then V1 over T1 equals V2 over T2. Pressure law, P1 over T1, P over T equals K. Then P1 over T1 equals P2 over T2. Here, lambda T equals K. Since lambda T equals K, lambda 1 T1 equals lambda 2 T2. Right? Take it down. Take it down. Okay, right? Now from here, uh, we have come to the end of all the theory parts in BLACKBODY radiation, right? And hereafter, we'll discuss few sums and most importantly, graphs, right? Sums and graphs are coming up. All the theories are done here at this point. Okay, go to question 7 on tute. Go to question 7 on tute. Question 7. Go to question 7 on tute and try it. Give it a try. Question 7. Start question 7. Give it a try. It says a black body at T Kelvin's temperature radiates at a rate of 10 millivolts. What is the rate of radiation if same body at of same body at 2T Kelvin temperature? Right. Give it a try. Question 7. Right. Question 7. right? Okay, we are getting answers. Let's see. 20, 160. Right. So apply this for these two scenarios given. Right. What are the given data? A black body radiates at a rate of 10 millivolts. Okay. Then apply Stefan's equation. We have only two equations in black body radiation. Only two. Right. Only two. Then from Stefan's equation, Q over T equals sigma A T to the power 4. Right. Sigma and A are common for the same body, no? So which means uh, I have discussed these things in questions and other paper classes and everywhere. QOT is proportional to T to the power 4. Apply this for these two scenarios given. First case, 10 millivolts is proportional to T to the power 4. Second case, let's say Q over T proportional to 2T to the power 4. 2T to the power 4. Right, divide these two. Divide these two. Right, then Q over T over 10 equals 16 T to the power 4 over T to the power 4. These two cancels. Q over T equals 160 millivolts. 160 millivolts. Right? A simple one. Very simple one. It's a simple one. Take it down if any changes. Take it down if any changes. $20 millivolts. No, not 20. 160. Okay, right? So if you have finished that already, go to question 8. Go to question 8. A spherical shaped bulb of 100 watts and radius 10 centimeters is hung by a ceiling as shown. The bulb distance between the bulb and floor is 2 meters. Consider Stefan's constant as sigma equals 5.67 10 to the minus 8 and consider bulb as a black body. Right, that's what I told you. Now when it comes to questions, for the ease of doing the question, will be given the objects as black bodies. Then we can use all equations of black bodies, right? If you are asked to if you are asked to consider this given bulb as a black body, then we will use it, right? If not, E will be given as 0.8, 0.5, something like that simply. And if it is about sun, let's say, then if you are asked to consider sun as a black body, then we will consider that as a black body, right? Say something burning, right? A ship is burning. A ship is burning, and we are doing something related to the ship, right? A calculation. Then in that particular question, you might be asked to consider that burning ship as a black body. Then we will consider. So likewise, for the ease of doing questions, we will consider them as black bodies, right? Okay. Consider as a black body. Determine intensity of heat radiation at the surface of bulb. Okay. Try first one. Right. Let's go part by part. And one small thing, this 2 meters should be marked from the surface like this. 2 meters should be marked from the surface, not the center, should be from the surface. A small thing. Okay, try part one. Try part one. Determine intensity of heat radiation at the surface of bulb. Right? Okay, any answers, anyone? Okay, let's see. We are getting answers. Let's see. We are getting answers. Right. From the surface of the bulb. Now, Stefan's equation cannot be applied yet because temperature is not yet known. Right? Temperature is not yet known. But voltage is given. Voltage. Voltage is a power. Voltage. Voltage is given. Right? This is given as 100 watts. No? 100 watts. Right? Voltage is a power. Right. Then we know intensity can be written as what? P over, oh, let me write this way. Now, in the question, 1 second, it is asked about intensity of heat radiation. Okay, intensity of heat radiation. So we know intensity of heat radiation is given by E over TA, right? But E over T is power. Then this can also be written as E over T is power, no? T over A. Then power is given 100 here. Area of a bulb. Area of bulb means area of a sphere. Area of a sphere is 4 pi r squared. Right? Area of a sphere is 4 pi r squared. Right? Area of a sphere is 4 pi r squared. Right? Then 4 5 22 over 7 r squared. R is 10. That is 10 centimeters. Then 10 to the power minus 2. This whole thing squared. Simplify this and see. Right? Keeping the final answer up to 2 decimals is enough. It would be enough. Right? Then this is 700 here, 88 here, and 10 times 10 to the power minus 2 is 10 to the power minus 1, then 10 to the power minus 2 here. Right. Seven point nine five. 7.95. 7.95. 7.95. 10 to the power 2, no? 10 to the power 2. So that is 795. 795 Wm minus 2. 795 Wm minus 2. Right? 795 Wm minus 2. Right? Go to part 2. Go to part 2. Part 2. Determine temperature of the bulb. Determine temperature of the bulb. Give it a try. Temperature of the bulb. Any answers? Give it a try first. Give it a try. (1.402 10 to the minus 6). You are saying in kelvins? I don't think. Cannot be that much of a less kelvins value if you have given it in kelvins. Square root 4. Square root 4 have to simplify. That's a log simplification there. That's a log simplification. Right? In the exam, you have to do a log simplification. Right? So if that came, the only option is log. How to simplify it using logs. Okay, let's see. Since answers are coming. Right, now we can apply Stefan's law. Stefan's equation. Q equals sigma A T to the power 4. Right? And we have an answer here for I, no? For I. I is, we can create I here, Q over TA. Q over TA is I. Then sigma T A to the power 4, sigma T to the power 4. So we know Q over TA is intensity of heat radiation. Then I equals sigma T to the power 4. This is 795. Sigma is given 5.67, 5.67, 10 to the power minus 8, 10 to the power minus 8, t to the power 4, right? Then t to the power 4 equals 795 over 5.67, 10 to the power 8. I will keep 10 to the power 8 as it is, because when we take the fourth root, right, when this is a divisible, when this is a number divisible by 4, it is easier. Then t should be 795 over 5.67, right? 1/4, right? 1/4 into 10 to the power 2, right? This is a log simplification. This part is a log simplification, right? That we have to do using logs, right? That's how in the exam it happens. 795. $3.44. This is 3.44, 10 to the power 2. So this is 344 kelvins. 344 kelvins. That's a reasonable value, a normal value. 344 kelvins means it is around 65, 70 degrees Celsius. No? So when a bulb is lit up, so usually temperature rises to 60s, 70s, 80s, likewise. So this is the value. 344 kelvins. 344 kelvins. Right? Take it down. Others, if that is finished, you can go to part 3. Right? If that is finished, you can go to part 3. Intensity of heat radiation on unit area on flow due to bulb. Intensity of heat radiation on unit area on flow due to bulb. Right. Any answers? One point nine. 1.9. Others? Let's see. It's possible. Let's see. Right. Listen. Now, always we consider this spread of heat radiation as spherical, because when there is starting from the surface, right, it is going to spread all around, no? Right? It is going to spread all around, right? Then if that is reaching the flow, which means it should reach to a sphere of radius 2. It should reach to a sphere of radius 2. Right? Intensity is asked. Then again, intensity is E over TA. E over TA. And E over T is given, right? E over A, right? And apply this. P is 100. When you write area, this is the area of the sphere of radius 2 meters, because always heat radiation spreads all around in all directions. So the distribution is spherical. Distribution is spherical. Right? Area is 4 pi r squared. Then 4 phi r 2 meters, then 2 squared. Simplify this. 2 squared is 4. Then this is 25. This is 25 times 7 over 88. 25 times 7 over 88. 1.98. 1.98 Wm minus 2. 1.98 Wm minus 2. Good. Last part. Go to last part. Energy of heat radiation absorbed by unit area of flow during an hour. Energy absorbed by unit area of flow during an hour. Right? Energy absorbed by unit area during an hour. When it comes to blackbody radiation, listen, when it comes to blackbody radiation, it is very much manageable, because we have only two equations, only two, right? Two laws, Stefan's law and Wien's law, right? Other than that, the only equation we'll be using is this equals ida, right? Two laws, Stefan's law and Wien's law, and if you need to connect intensity with power or something like that, then we are using equals ida, equation of intensity. Right, part 4. Okay, right. We are getting some answers. 609, 69.4, 475.2. Why do you say watt seconds? Watt seconds means joules. No? Watt seconds means joules. Yeah, that is an energy. Should be in joules. 475.2. Let's see. Right. What's the question? What's the question is about energy of heat radiation absorbed by unit area of flow during an hour. Right. Then we can apply this equation again to flow. To flow. Right. To flow, I equals E over TA. Right. To flow, I equals E over TA. Right. Means E equals IDA. Equals IDA. Right. Now I at the flow is known. That is this value. I at the flow is known 1.98 during an hour. Then 3600 seconds into area. Unit area means 1. Unit area 1. What's coming? 1.98 into 36. 7,128. 7,128 joules. 7,128 joules. Right. So likewise, with our requirement, based on our requirement, you can apply equals IDA for any surface, for the bulb or outside the bulb to the flow. Likewise, that is applicable anywhere because that is not a blackbody equation. This is not a blackbody equation. This is general equation of intensity. Blackbody equations are Stefan's and Wien's law. Right? That is only for black bodies. Right? Take it down. Okay. Raise your hand if that is clear enough. And ask if any questions. Raise your hand if that is clear enough. And after Mandan edition is also finished, I will put these questions, right? I will put questions from this unit also in your papers. So how A equals on unit area. Unit area means 1 square centimeter. Unit area. Unit area means 1 square centimeter. It is given as a unit area. Unit area. Right? Any other questions? Okay, is it all clear? How is radius 2? Because heat radiation distributes spherically, three-dimensionally, spherically, all around the point. So is it must to take the value into 2 decimal places? Yes, that's a standard we have in A levels. It's a standard we have in A levels. What else? Any other questions? Right. Okay, so if you got any questions, you can ask meanwhile as well. Okay, let's move on. As a heading, write down graphs in blackbody radiation. Graphs in blackbody radiation. Graphs in blackbody radiation. Right? This is not a big deal. This is not a big deal. I will give you the access, right? You know how to plot graphs, right? You have to start from the first one and complete all graphs, right? Graphs in blackbody radiation. Right, graphs in blackbody radiation. Use our graphing techniques. Use our graphing techniques. First one, Q over T. Q over T with T. Second one. So you can take down and start, right? Plot them one by one. Second one, Q over T with T to the power 4. Next one, Q over T with T squared 4. Q over T with 1 over T to the power 4. 5. So when you send me answers, right, since that is about a graph, you can send the name of the standard curve, like y equals mx or mx plus c, mx squared, mx to the power 4, or inverse. Likewise, that's better, no? Right. 5, q over t with 1 over t. Next one, 6, 1 over q over t. 1 over q over t with t to the power 4. Okay, start now. Start. I'll start in like 3-4 minutes. Okay, is the rhyme enough? What are the shapes? Shall I start? First one, Q over T with T. Then use Stefan's equation. I'll be doing the simplification here. Right? Yeah, here. Q over T equals sigma A T to the power 4. T is X. Then this is X to the power 4. Whatever it is has a product with X is gradient. And this is as Y. Y equals mx to the power 4. That's a standard shape. Right? Second one, Q over T with T to the power 4. Q over T with T to the power 4. Then if I do it here, Q over T, sigma A T to the power 4. Now this whole thing T to the power 4 is given as X. Then this is gradient. And this is as Y. Y equals mx. So a straight line goes through origin. Next one, Q over T with T squared. Then Q over T equals sigma A T to the power 4. Rearrange this using T squared. Then sigma A, this can be written as T squared no, T to the power 4. T squared is given as X. Then T squared is X, this is X squared. Whatever it is as a product with independent variable is gradient. This is Y. Y equals mx squared. Y equals mx squared, standard curve. Right? Next one, Q over T with 1 over T to the power 4. Q over T equals sigma A T to the power 4. Create 1 over T to the power 4 without harming the equation. Right? We discussed. Then this can be written as 1 over T to the power 4. 1 over T to the power 4. No harm. Right? Then 1 over T to the power 4 is given as X. Right? Then this is Y. And 1 over T to the power 4 is X. So this is 1 over X. 1 over X, whatever it is as a product with this is a gradient. Y equals m1 over X. That's the inverse curve, a standard curve. Inverse. Q over T with 1 over T. Then Q over T is sigma A. This can be written as 1 over T to the power 4. No? Now I need 1 over T. Create 1 over T again. To create 1 over T, this is 1 over T whole thing to the power 4. No change. No change. Right? And 1 over T is X now. Then this is 1 over X to the power 4. Gradient. And this is Y. Y equals mx to the power 4. Y and X are inverse. Any inverse curve has the inverse shape. Right? Last one, 1 over Q over T with T to the power 4. Then our equation we know is Q over T equals sigma A T to the power 4. Sigma A T to the power 4. Then I need 1 over Q over T. Right? 1 over Q over T, not 1 over 1 over 1 over Q over T. Then we can write it as 1 over Q over T. Right? Sigma A T to the power 4. Then 1 over Q over T is Y. So this is not Y, this is 1 over Y. Right? And this whole term is X. And this is gradient. Y and X are inverse, which means there is an inverse curve, a standard shape. Right? Take them down. You should be able to plot all these curves using graphing techniques, right? This is all about graphing techniques. All about graphing techniques. I haven't used anything other than graphing techniques. Right? Then start the next set. Start the next set. Seven. Lambda with T. 8. Lambda with 1 over T. 9 1 over lambda with 1 over t. 9 1 over lambda with 1 over t. Right? 10 1 over lambda with t. Right? Then 11 lambda with t squared. Lambda with t squared. 12 12 lambda t with lambda t with t. Right, try them. Seventh one. 1 over q over t, no? 1 over q over t is given as y. 1 over q over t is given as y. Now here I have 1 over q over t. Then for this 1 over 1 over q over t, no? 1 over q over t is y. So that is 1 over y. Make it again. 1 over q over t. Isn't this whole thing y? That is y, no? So this is 1 over y. Right? I will start in 2-3 minutes. Try them. Right? Lambda with t. If you are putting lambda with t, right? Our known equation is this. Lambda t equals k. Wien's equation. Lambda t equals k. And subject lambda is k 1 over t. Right? T is as x. So this is 1 over x. Gradient y. Y equals m1 over x inverse. Right? Second one, lambda with 1 over t. So we know lambda is k times 1 over t. No? Now whole thing 1 over t is given as x. Gradient y equals mx. Right? 1 over lambda with 1 over t. Then I have to create it. Because what we have is lambda equals k 1 over t. 1 over t is already here. Then to create 1 over lambda, 1 over lambda is k 1 over t. Right? Then 1 over lambda is 1 over y. Gradient 1 over t is x. Y and x are inverse. That is still an inverse curve. 1 over lambda with t. 1 over lambda with t. Then what we know is lambda t equals k. Right? Then lambda t equals k. Put this to the other side and create 1 over lambda. Then 1 over lambda equals t over k. Right? Then 1 over lambda equals 1 over k times t. T is x. T is x. 1 over lambda is y. whatever it is as a product with this gradient y equals mx. Lambda with t squared lambda with t squared, right? Sorry, small mistake. Lambda with 1 over t squared. Lambda with 1 over t squared. Sorry, lambda with 1 over t squared. If you have plot lambda with t squared, it will be an inverse curve, right? If you plot lambda with t squared, listen. If you plot lambda with t squared, it should be an inverse curve, right? Now, no need to erase. As the next number, plot lambda with 1 over t squared. That is what I wanted to give. Lambda with 1 over t squared. Then what we know is lambda is k 1 over t. Then we can create 1 over t squared like this. This can be written as 1 over t whole 1 over t squared whole thing root without doing any harm to this equation, no? Right? No harm to the equation. Again, if you simplify this comes no harm to the equation, right? Now 1 over t squared is x, which means this is root x, and this is gradient m y. M root x, a standard curve. This t with lambda t, right? So what we know is lambda t is a constant. Lambda t is a constant. If lambda t is a constant, whatever the value t takes, lambda t is a constant, right? Simple graphing techniques. I'll be soon conducting the graphing seminar for 27 batch, right? Now, being in 26 batch, still if you are not comfortable with plotting graphs, right? You can get to know about the date and time from the channels, right? It will be coming up sooner, very soon, right? And you can join that day if you are still not familiar with this, right? Or else another option is the last year graph plotting seminar is still on YouTube. You can go there and watch it as well. This time one for 27 batch I'll be conducting soon, right? So if you are not yet comfortable with graphing, join that seminar and get familiarized yourself with that, because you are just 22 weeks ahead of the exam now. 22 weeks, just 22, right? There's no any other time to wait and see. There's no time to wait and see, right? No time to wait, no time to think. You have to action. You have to action. You have to take actions. You have to take actions. You have to act. Right? Finished? Right. Okay. Now with this, we have come to the completion of black body radiation as well, which means radiation part is done. Radiation part is done. And next day plan is we are starting the new part, next part in Madan radiation, that is called photoelectric effect. Photoelectric, right? So we'll be starting photoelectric effect next day. That's a main main part to be covered next day, photoelectric effect. And the other parts coming up in Madan radiation now, photoelectric effect, X-ray production and laser production, right? Those are the coming up parts. And next week we are starting photoelectric effect, right? Any questions about the things we discussed today? Go through these things again, because you are hearing these things for the first time, not something familiar as what we do in mechanics, those things, right? These things are new to you, right? But they are very much simple to be understood, very much simple to be understood. That's why we can easily score in these kind of units. Okay, seems no questions. If no questions, we can wind up. Right, is there any? What about the ones on YouTube? All good? Is it all good with all of you? All clear. Right. So if it's clear, we'll wind up. Right. We'll wind up. In this class, in the reverse class, we'll be starting photoelectric effect, as I told you, and the next S2A discussion will be on viscosity. Right. I will inform the time and date sooner, and about the graphing seminar, that's also coming up. Right. There are more things, and optics practical seminar is also coming up for 26. Optics practical seminar, that's also coming up very soon. Right. So there are more things roll out in these coming months, because we are now at a high time, just 22 weeks ahead of the exam. Right. 22 weeks. Right. That's a high time, 22 weeks and 1 day now. Okay. Then if no questions, we can wind up. Stay safe and work hard. Right. Most importantly, work hard without wasting your time. Right. Every second, each second matters. Right. Each second counts. Each second counts. Okay, then work hard and let your results speak. Right. Work hard. You can work hard in silence, actually. Work hard in silence. Right. No need to like say anyone that you are doing this and that and all that. Right. Work hard in silence and let your results speak. Right. Okay, then we'll wind up. Good night and goodbye. See you.